So today we'll discuss week 7 content. Unfortunately, because the neural network, deep learning, and convolutional neural network, they take a lot of time uh, to train the model. So we'll not be doing any of the programming exercises today. What I will do is, if in some other week, in some other coming week, we have some kind of a lot of theory class, not very interesting. Then I will introduce in that class the example for programming example for ANN and CNN. But for today, we'll discuss just the theory of ANN and CNN, apart from the other content that were discussed in the session. Okay, so let's start. Yeah, so mainly in this week's discussion, we discussed about calibration and validation. Yeah. And we discussed some type of calibration and validation processes. Particularly, uh, the more interesting types were data subsetting type of calibration and validation. So let's look at that. First, we had random holdback or holdout. What does that mean? That it will randomly either hold back some of the data sets or hold or give out some of the data sets for calibration and validation. Basically, why we need all these things is when we have only one data set. Let's say we have X and Y. We have only one set of data. It contains lot of points, but we have only this, and now we want to train our model or we want to make a model. Then we divide this data set into calibration and validation set. So that is what we are doing in this random holdback or holdout. So when we say random holdback, so you can imagine that it is holding back some of the data sets for later for calibration and giving out some of the data. Holding back the data set for validation and giving out some of the data for calibration. So it's the simplest kind of cross validation. That's that's good. That is the good thing going for this technique. And so one thing to keep in mind when we are doing this random hold back or give out kind of calibration and validation, that yeah, Prachi, can you mute your mic? I think some disturbance is coming. Thank you. Okay, so one thing to keep in mind when we are using a random hold back for our calibration validation purpose is that the calibration set must include the extreme of the dataset, extremes of the dataset. So what I mean is that if you have, let's say, some points and out of these points you want some of the points to be used as calibration to fit a line as we have shown here. So let's say I'm using these red ones for calibration. Now we'll get some kind of line using this model. But when we go for validation, see, this line was trained on the data set that is limited to this extent. So we can say it is good for predicting the response in this extent. If we go outside this extent, let's say for these values, it has to perform extrapolation. So to avoid extrapolation, we have to make sure that these extremes, the maximum and minimum, are included in the calibration dataset. You can ignore the other points, but you need to have the extreme. Okay. Now here's another problem with the random holdout method is that it will give high variance when it comes to the validation dataset, validation process or validation test, you can say. That is because the random holdout will give you randomly some of the points from this data set. Now, based on that, how the random points were chosen, you can have different set of lines that can be fitted here. If you let's see, for these points that I have chosen, we actually wanted this black fit as the desired line, but since we have these the red points in our calibration data set, we'll end up with something like this. And when you put these values, put the other validation data set into this calibrated line to check the error, you are going to get very high errors. So this is one of the demerit, one more of demerit of the random holdback method. So to avoid that, one way is one method to avoid that is k-fold validation. Okay, so how does this k-fold validation avoid this kind of uh, high variance? So let's understand using another example. Let's say you have set of points that describe relation between x1 and x2. Now these set of points are arranged such that they are making some kind of shape. Now the k-fold says that you divide this data set into k subsets where k is greater than 1. Now let's say our k is 3. Then we have to divide this data set into 3 subsets. So one is green, one is red, and let's say one is this blue. Now what we do is, let's say we take first time, let's say we keep the red data for validation and we use the green plus blue for calibration. So in this case, from the red data, we will get some kind of error, specifically let's say sum of square error. Now we do the validation calibration again, but in this case, we take the blue data for validation and we take the red plus green for calibration. So SSE1, SSE2. In third case, we and now you uh, would be realizing that we are going to take G for the validation. and we are going to use red plus blue for calibration. So basically what we did is we performed this operation of calibration and validation k times, and every time we took one set of among the k subsets for validation while using the other for the purpose of calibration. So this what this helps us is, now we can be a little bit sure that the error or the uncertainty from the initialization or the random selection is gone. The uncertainty due to random selection of calibration data is gone, because all the data at some point of time is going to be used for our model calibration, and the error is given by average of the three errors. So, and in that case the variance also for the validation is reduced. Okay, so here we did k-fold data set. So let's say in our this maybe 20 data set, we divided into 3. Now an extreme case of this k-fold data set is that we divide the data set into the number of subsets that is equal to the number of data set itself, number of observation itself. So here if we had, let's say, 20, now what I do is I divide my data set into 20 subsets itself. That means each point is a subset. So we can do that, and that is called LOOCV, leave one out cross validation. Means leave one out, use others for calibration, and the one you left out, use that for the purpose of cross or validation. Okay, just a minute. Yeah. So I don't have that many colors, but you can. Oh, I didn't write that. Let me write the topic first. So the third type is leave one out cross validation. So what we did, let's say this is 20 data sets. You can count it if you want, and I divide the 20 data sets into 20 groups, 20 subsets. So that means that k is basically 20. Now what we do, the first time we'll take this for validation, and we'll take other 19 for calibration, and we'll do this same process 20 times. So this is the basic behind the leave one out cross validation. Okay, and this is supposed to be good for if you have less amount of data. Let's say you have less data set, then it is considered good. Okay, so this is about the data subsetting. So when you are using the same data set for training your model and then validating your model, then these are some of the techniques that you can use to divide the data that were discussed in the session. Okay, now coming to again the process of avoiding how to like overfitting and underfitting. So for that, like in linear regression, uh, we we also see overfitting, underfitting when we have lot of features, right? So to avoid that, we discuss some of the things when we can use actually PCA or and multicollinearity. We can remove the multicollinearity between different features if there exists multicollinearity. So one more process to remove this multicollinearity or overfitting to keep our model simple is ridge regression. So let's discuss about ridge regression. Okay. So when we see result of our linear regression, so how does it look like? So let's say if we have n features, then our linear regression result will look something like beta naught plus beta 1 x1 plus beta 2 x2 plus beta n xn, where this is a bias and this is these are the beta 1 to beta n are the slopes for corresponding features. So this is the equation that we'll have for any linear regression result, right? The ridge regression also is going to give the same, but the difference is how we calculate the costs. So how did we calculate the cost in ordinary linear regression? We just calculated the square of the difference of the observed y value or the dependent variable and the predicted dependent variable from our model. So let's say we denote the predicted as cap and yi as observed. So we calculated the error by the sum of the square of this difference. Now, what can happen in this case is we'll understand with the problem, but I just want to say intuitively, if you try to understand that what can happen in this case is if you have one feature that is very closely related to your predicted value in some cases, and unfortunately you end up choosing those more of those points where this one feature is closely related to the predicted value. Unfortunately, if you are using these more of these points in your calibration, then what will happen, your beta 1, that is the coefficient for that feature, is going to be given more weightage. And let's say if in your validation set you don't have many points which actually show this that same strong relation, then you'll end up with high error in your validation. So this ridge regression is a way to increase the overall fitness or overall accuracy of the model. It will decrease the accuracy in the training set. 100% it is going to decrease the accuracy in the training set, but we don't care much about the training set. The model's accuracy or model's wellness acceptance is governed by the accuracy in the validation set. And we'll see that it tends to reduce the uh, error in the validation set. So let's look at this through an example, a simple example, no need to use any calculators. So let's say if we have a y predicted a dependent variable and x1 and x2 are independent variables, and the values we have some data points. Let's say we have 2, 4, 9, 11, 3, 7, 1, and 0.95, 1.99, and 4.51, 5.48, and then some values. Now you may be able to guess where I am going with this, but let's just keep it that let's just do this so that other people will also understand. Some of you might be able to understand. what I am going to do. So let's say you have this data set. Now, if I use, oh, sorry, if I use these examples for my calibration, and I am going to use these examples for my validation, then the question I want to ask you guys is, looking at this, if I ask you, what value of beta 1 should we keep here using this calibration? What would you guys suggest me? What do you guys think is a good value for beta if I am trying to calibrate my model using this data set? Beta 1 actually. Leave beta naught and beta 2. Just look at the values of y and x1, and you can easily guess that there is a value in fact. Okay, 2. Very good. So Shruti Namdeo has told correctly that beta 2 seems to be somewhere around 2. And that is what is going to happen. Your model, when you train it, it is going to give you somewhere around 2, and then these values will be very less. The beta 2 and beta naught are going to be very less. These are not the exact values if you try to fit the model. I'm just saying roughly this is something what you may get. But now if you go for validation, so then you will see that that particular relation is nowhere to be found in this x1 and y. So to represent it graphically, if this was my x1 y1, sorry, x1 y, and let's say this is 1 2 3, this is 2 4 and 6. So the line that this model is fitting, and if you take the projection of that line on this x and y and x1 plane, it will look something like, maybe it will not go directly, but it will look something like this. It is going to be y equal to 2x1 plus something x2. It is going to follow that trend. And when you go for validation, so as we can see from the validation data points, that the validation points will lie somewhere around here, and 7 and 5 somewhere around here, and 1 and 0. So this is going to give a high error when it comes to the uh, validation point. So to avoid that, we use ridge. To avoid that, we use ridge regression. What it does is it gives a error. It modifies the loss function or the error function that we have seen here of the ordinary linear regression by adding one bias in that. So we have normally something like this. So in that we'll add a bias, that is sum of square of the coefficients of each feature, and this is called bias, or in PPT it's called penalty term. And this lambda is a factor that you can choose. We'll see how to choose this lambda in few minutes. So we have to choose this. What it basically does is it will try to rotate your fitted line. So this is the line that you have at lambda is equal to 0. Now when you have some lambda and you have added this beta square into this error function, then it will try to reduce the error. Always the training process is to try to reduce this error between the predicted and the observed values. So when you do that, graphically speaking, it tends to change the value of beta 1 and beta 2 and beta naught, and in doing so it changes the slope of the line and aligns it in such a way that the sum of square of the in the calibration also is less. It doesn't know about the calibration data, but it ends up happening that the overall accuracy is increased by the decrease in the uh, error in the calibration data set. Now, one more way to understand this, how it is helping us, is through this process. Let's say instead of this relation being 2, instead of this beta 1 being 2 from the equal to 2 from this relation, if it was 200, if we had something like these values, then in that case you can imagine that our model will keep the beta close to 200, and the other parameters are going to be negligible compared to the beta 2 and beta naught are going to be comparatively negligible when it comes to the equation. So you can just approximate your equation as y equal to 200x1, but that will give very high errors in the validation. So when you have this such a high beta, then that is going to increase the error also in your ridge regression. So in that way, this also helps that it keeps the dependency of the predicted value on each variable not so high that it gives overfitting, and not so less that it gives a huge error in the calibration also. So as you can see, if it is 200 square, then lambda it is or yeah, lambda it is going to give very high error or very high loss. So it will try to reduce the beta, at the same time it will try to increase the so it will try to reduce beta 1, at the same time it will try to increase the beta 2 and beta naught to get some value so that the error is less. I'm not saying that it is not going to completely ignore this 200. Relatively, still this beta 1 will be higher, but beta 2 and beta naught will not be negligible in this case. So in that way, we prevent overfitting that can arise from this set of data. And you can try different values of lambda. So let's say if this was some lambda 1 is equal to 2, and you can try different lambda of equal to 5, right? So one thing also to note here is that if lambda is too high, lambda is very high, then in that case your loss function will actually be governed by this term rather than the it will be governed by this term rather than this, which you actually want to minimize. So we have to actually be careful about where we want to keep our lambda, because if your lambda is too high, then more weightage to will be given to reducing the coefficients. So basically it can give you as y equal to 0.01 x1 plus 0.001 x2 plus 0.03, like that, because in this case this term is very low. So our according to this model that we are training, the error will be less in this particular case. So we have to do iterative process or AIC BIC to get the proper value of lambda. Okay, so before we go to lambda, uh, there is one more method which is very similar to ridge regression. We will discuss that, and we'll check briefly about the AIC and BIC method to calculate the lambda. That particular method is called lasso regression. Okay. So what is difference? What is the difference between this lasso regression and ridge regression? Regression. Okay, before I go to the lasso regression, one thing to note is this process of adding this penalty term is called L2 regularization. Some nomenclature is there, but you can just memorize this. And this lasso regression will have L1 regularization. Okay, so what's the difference apart from these two L1 and L2? So the difference is in the cost function again. So with the cost function now is modified into this. Instead of adding the square of the coefficients into the cost function, we add the absolute value of the coefficients. So and other processes are same. It also rotates the value. So what are the major differences between what is the major difference between lasso and ridge? Is that it can remove the features actually that are so it can remove the features that are related to some other features, like it can remove the multicollinearity. So it can remove overfitting through feature selection. It can remove the features. We can just let's write here. It can perform feature selection. Right, remove overfitting. That part can be done by our ridge regression also. But when we say remove features, what do we mean by remove features? So when we have an equation like this, so end equation is going to be same. End equation is going to be same for from all these methods. So when we have this equation, when I say it is going to remove a feature, it means that feature is not going to be used in our validation process. And the only way that can happen is if the beta of that feature or the coefficient of that feature becomes 0. So that is something this lasso regression can do. What ridge regression can do, it can make the beta very small, but it cannot make it 0, whereas this lasso regression can completely eliminate that uh, feature from our regression equation. There's just something to keep in mind. Okay, now how do we predict lambda? How do we choose lambda? So one basic or one simple layman process of choosing lambda is just try out different lambda and then make a plot of your validation error and lambda, and you can then choose the lambda for which this validation error is the least. That is one way. Another way is to calculate your either AIC, that is I forgot the full form, let me check. A Kike's information criteria or Bayesian information criteria. A Kike's information criteria. So this is calculated using the equation minus 2 times of log likelihood and plus 2 into number of parameters, that is shown by k in the PPT. So number of parameters including the bias also, and L is the log likelihood. Okay, sorry. The formula for log likelihood is, so the how do you get this value, this particular value, not only log likelihood but the whole value minus 2 times of log likelihood. I searched for this in the internet and I got that it will be equal to n ln sse divided by n, where n is the number of data set, basically for validation only. And SSE is just the sum square error that we have seen above. So this is the AIC. We will not go into the detail because how this process is, these two parameters or these two quantities are just used for selecting the lambda, which is not even that important. You can select lambda from the trusted old method of just trying different lambdas, because so we'll not go into much detail. I'll just share the formulas of these things. BIC, that is Bayesian information criteria. It has similar formula if you look at it carefully. Just the difference is it has, instead of 2, it has log of n, and n being the same number of data set for validation. It is written slightly differently in your PPT, but you can use this also. So how do we do, how do we use these AIC or BIC? You don't use them together. You can use either AIC or BIC. So you just, again, as like earlier, we use different lambda and choose lambda when AIC and BIC are small or smallest. Similar procedure as normal SSC. Okay, so that's how you choose your lambda. And now we have covered the part of linear regression that was discussed in the week 7. Let's come to the topic of neural networks. So, artificial neural network. Yeah, this is. So there was quite a bit of biology that I am not going to cover regarding dendroids and cell body and all. We'll just cover basically what we see in our neural network. Okay, so neural network basically is a set of simple linear equations or operations, yeah, occurring many times. And when this happens, they are able to capture even the most complex behaviors that are observed. One thing that has become more common when it comes to after this boom of this neural network and machine learning is that people just use these techniques without knowing much of the math. They'll just have some data set and some value corresponding to it, and then just fitting some model and then publishing papers, which is not very good. That's why some of the good mathematicians also don't like machine learning that much. You would have seen some of the memes in the internet where they show that no, machine learning is cheating, whereas statistical learning is the actual learning. Okay, so we'll not go into that debate. So how does this neural network works? So it has one input layer, it has one output layer, and one or more hidden layers. Now, if the hidden layer is one, as I told in the first class, I think, if hidden layer is one, it is called shallow neural network, and it is greater than one, it is called deep neural network. Okay, deep learning also it is called. Then the process of learning is called deep learning. So, what is this input layer actually? Input layer is nothing but your input parameters. So this is nothing but the value for this will get the value for x1, this will get the value for x2, and so on. The last neuron will get the value for xn. Okay. Now, what will happen is these all neurons. So let's call them neurons or nodes, whatever you are comfortable with. You can call them what you want. So these all nodes are going to influence all the nodes that are present in the hidden layer. So let's say if our hidden layer has three nodes and we have only one. We have only one hidden layer and it has three nodes. So all these input values are going to affect this hidden layer, each node. And how to do that? How that will happen? So let's say this node has a value z1. So it will be governed by these nodes as w1 x1 plus w2 x2 plus wn xn plus b. So these are the weights that is assigned to each node when it comes to this particular node in the hidden layer, and this b is the bias, also one of the parameters that we'll need to train. And similarly, the Z2, let's say if we want to talk about the second neuron in the hidden layer, this one. So it will be something like Z2 is equal to W dash 1 x1 plus W dash 2 x2 plus W dash n xn plus B dash. This value is going to be given to the second neuron. Now, how to represent this? The network that you see, how does that come? That comes through this process of weightage only. So, this is W1, this is W2, W3, and so on. We have this network, and when it comes to this is W-1, W-2, and so on for this interconnectivity. And the best way to represent this connection between two layers, the concise way, is a matrix, and we call that matrix or this connectivity as capital W. That is a matrix W1, W2, Wn, W1 dash, Wn dash. Let's say we have three, so double dash, Wn double dash. There is a more accurate way to write this. You can actually write it as W11, W12, W instead of dash. You can have nicer way to write these things, but you can explore these things on your own. So this is the weightage matrix or the W or the linking matrix that we train. So we have also the bias matrix, capital B, B, B dash, B double dash. So these two matrices actually describe the relation or the dependency of the hidden layer neurons with the input layer. Now you will have the same kind of interlinking if you go from the hidden layer to the output layer. Let's say if it is a classification problem, right? it's a classification problem. In that case, this output layer, I will come to the activation function just in a minute. So in the classification problem, it will be like yes or no, binary classification problem. So it will be one neuron. Let's say it is one neuron, and if the neuron value is one, then you say yes, and the neuron value is zero, you say no. So you have only one neuron which can take one or zero, two values. So in that case, these three, sorry, I'll just use the highlighter. These three will be giving their weights to the particular neuron. You can also represent that in terms of a matrix. Rather, it will be a vector because it will it won't be a matrix. It will be just W11 in this. Yeah, it will be the yellow will be W11 and the blue will be W2, or let's call it not W but V1, V2 and V3. So this W2 matrix, let's call this W1 V1. This W2 matrix will be V1, V2, V3, and similarly B2 will be something like C1, C2, C3, the bias matrix and the weighted matrix. So you can see that these nodes or the neurons are related to the input layer through some matrices. And now let's come to the activation function. Now what we'll do is we'll draw it here much more cleanly. So we have these many, let's say four, and then we had three, and then we had one. So now what will happen is, let's say you have some weights now. Now you gave some value for x1. So it will take integer input, of course, that should be obvious. So you give some value for x1, x2, x3, x4, and then based on that value, you calculated some value for z1, you calculated some value for z2, calculated some value for z3. In case of neural network, these neurons don't actually use the hidden layer neurons don't actually use the exact value of this z1, z2 and z3. Rather, they convert these values to an activation sequence. The hidden, let me write it here, the hidden neurons convert the real values to activation sequence. Okay, so what does activation sequence means? So that is where activation function comes in. So you put this value of z1 into a function, let's say g. Sir, output comes only in class 2 yes or no values. So you can train your. So if you want to ask it more clearly, Shruti, you can unmute and ask because I don't understand this question very specific, clearly. Or if you want to type again, you can raise your hand and type so that I can wait. Shruti. Okay, maybe. Yeah.
Yes, sir.
Yeah, can you ask your question?
सर माय क्वेश्चन इज कि आउटपुट लेयर सिर्फ दो ही क्लास में ही आ सकता है क्या, यस वैल्यू में और नो वैल्यू में? अगर अपना आउटपुट मोर देन 4 या 3 क्लासेस में डिवाइड है तो उसको कैसे अपन आउटपुट जनरेट कर सकते हैं?
Okay. So to tell to others, what Shruti asked is the output layer. Why does the output layer only have one neuron? Basically, if it is one neuron, then we can have one and zero. But if we want to have, let's say, not only 1 and 0, but some values, even let's not say like 3 4 values. Let's say we have real values, infinite number of values that can be expected from the output layer. So how do we do that? So to understand this, we have to first understand that I only kept one neuron for this, for the simplicity of this example, in the output layer. So there can be number of neurons in the output layer. That's one thing. There can be number of neurons in the output layer, and what you can do is you can assign this particular neuron to 0, this to 1, this to 2, this to 3. If you have some kind of classification problem, you can do this. But if you have and so that is the answer for Shruti, that you can have more number of neurons to assign the different classes if you have more than one class. Okay. Now, uh, coming to let's extend this question to understand one more thing that is actually related to the activation function. Okay. So now what if I want to predict some real numbers from this output? I i don't want to predict just 0 and 1. I want to predict also point 0.1, point 0.2, point 0.3, and then 1.2 until infinity if I want to predict. Then we have to use something called as a ReLU function, or you can just use identity function as an activation function for the last. So we'll see now how we do that. Okay, so one activation function that is most common in the hidden layers, that is a threshold kind of, that shows a threshold kind of behavior, that is called sigmoid function. So gz is a sigmoid. What it does is, whatever the value of z1, the output of this function, sigmoid function, is going to be between 0 to 1, excluding both the things. So it is, I would have shared with you this function in previous sessions. It will become asymptote to 1 and 0 for the positive and the negative extremes. Okay, so you can use this, and you can have, then you can have a threshold. So if the value that you are getting from, let's say it is a1, from this sigmoid function, if this value is less than 0.5, then this node will not be activated, and if it is greater than 1.5, then this node will be activated. We'll understand that also. How does that work? What is this activation and not activation means? So this is something you can use, but that here's the thing. Now when we use this sigmoid function, we have to give a threshold of 0.5, and our output is limited to 0 to 1. But if I were to use a ReLU function, that is rectified linear unit, that function looks something like this. That if my z is negative, then that function value is 0. If my z is positive, then the function value is z itself. Or you can, or if I were to use identity function, so if the z, a is actually z only, a is equal to z, that is the meaning of identity function, then in that case we'll have something like this, the relationship between a and z. So if I were to use this, then I can have real values for a and z, sorry, for the output from the this neuron, the output neuron, and in that case I can train my model to give the real values also. So to summarize whatever I said in order to answer Shruti's question, is that you can have, first of all, if you have classification problem, you can have more number of nodes in your output layer and assign each node to one class for your classification. Another, if you don't want to do classification and you want to do some kind of regression problem where your values are continuous, rather than discrete values. In that case, what you can do, you can use, instead of the sigmoid activation function, either ReLU or identity function for these output layers, and get some real values and then train your model. Okay, so it was quite a detour from the actual question, but I hope Shruti understood the solution, and rest of you guys also. Okay, so where was I? Yeah, okay, good. So now I said about activation and deactivation of the neuron. So what did I mean? See, when I'm using a sigmoid function, and let's say I got the value for a1, I'm using sigmoid function as of now for this hidden layer. I got the value of a1 as less than zero point 0.5, so I made it as, I deactivated this neuron. That just means that I assigned the value for this neuron to 0, whereas these neurons got the value of 1 and 1. Now what will happen in this case is, now when I'm going to compute my z for the output layer, it is not going to be affected by this neuron. It is only going to be affected by the other neurons. So what will it get? What will be the z value? It will be 0 into w, or v1, plus 1 into v2 plus 1 into v3. So as you can see, this neuron is not affecting the output layer or the subsequent layer. So we call this as deactivated. Deactivation is nothing but assigning the value to the node or the neuron as 0. Okay, so I wanted to talk about some more things. Yeah, and I will mention this again. When we train our neural network, artificial neural network, or anything, we are just getting the values of this matrices W1, B1, W2, B2, means getting the values of all these terms, so that we have less error. And how do we say error? Just the same thing, yi minus y cap square. Now you can train this model. So if you have come across any news, so I think I asked in some previous session, and you guys are familiar. Some of you were familiar with reinforcement learning. We'll not go into the detail of these things. I'm just saying that there are some techniques using which you can train your neural network to get the values of these matrices or the elements, so that this error is less. So it can be either stochastic gradient descent, normal gradient descent, and or reinforcement learning, genetic algorithm. All these things can be used. But basically, how do we train our model? We train our model by subtracting and minimizing the error, or the difference between the output that you get from here and the output that you already have, or the observed data. Okay, now here's the thing. It is said that, uh, okay, before I talk about deep learning, this ANN is this process of calculating this output value from these values is called feed forward. Why it is called feed forward? Because you can clearly see that first we gave the value of our input, then we went forward and calculated the values in the hidden layer, and then we went forward and calculated the value in the output layer. So it's kind of forward propagation is happening. That is called feed forward. Feed forward network. And there is something called back propagation. That is basically used to calculate the values of parameters. That means the capital W B, the matrices actually. And this is the most crucial part of neural network. So That is what I was saying, that you can train your model. So you can train your model using back propagation, which is in back propagation mostly people use gradient descent method for training the model. So we cannot cover all this um, concept of a neural network in this session. So for that, I'll suggest you guys, if you are interested, to go follow some YouTube lectures, because it's not simple. There are 12-week courses, 4-week courses, just to understand how this neural network is trained. A lot of complexities happen. Okay. Now, one thing, I want to justify one statement. So it was said that neural network can learn even the most complex responses or models. But to do that, we just have to increase the number of hidden layers. So how does that work? Let's look at this. How many of you are familiar or know about degree of freedom? Does anyone know about degree of freedom? Basic concept.
The number of movable link.
Yeah, very good. In structural engineering, we define degree of freedom as the number of movable links. Yes, and also, so if we our structure has a high degree of freedom, then it is very difficult for us to solve and get the stresses. See, if this is one point, and I this is fixed point in space, so it has 0 degree of freedom. It cannot move anywhere. So it is very easy for me to get this location with time, because it is zero, it will be fixed. Let's say if we have a pendulum, this is a fixed point. Now one weight is attached to a string, and it is allowed to move, and it will have angular degree of freedom. It can move in arc. So still it has some degree of freedom. I am able to predict it. Now if I make this as a rod, and I add another spring or another rod to it, and this is the point, and I want to know the position of this point. So you just imagine how difficult it is. As we increase the degree of freedom, this point can first rotate around this, and this point can rotate around this. So there will be like infinite positions that this particular point can take, right? It will be very difficult for me to predict these positions. Degree of freedom, basically it will tell us that how much variability your model can capture. Okay, and how does this degree of freedom increase when you increase the hidden number of hidden layers? So if we have, let's say, 3 input layers, and only one hidden layer, then uh, and let's keep it this way, only one output layer also. Okay, now this particular input can influence this output through two paths. One is this path, one is this path, right? Now if I include another hidden layer, which let's say just two nodes only. Now let's see how many paths this neuron or this value x can influence the output node. So this is the first path. Let's try to use different colors. First path, second path, third path, and fourth path. So you see the way, or the number of ways in which this input can influence this output has just increased, right? So there may be some model, which will not be having a straightforward relationship of this input layer with this output layer, or any of these input layers with this output layer. Now our model can capture, can have these four paths assigned to those four scenarios. Initially it would have been able to just capture, let's say, two scenarios, two extremes I'm talking about, but now it can capture four such scenarios. So we have increased the degree of freedom of our model, or the complexity of our model, by increasing the number of layers. And in that way, we are able to mimic more complex responses. And this is what deep learning is used for. Deep learning is good when you have some complex responses. But something, so I hope this is clear. Okay. So, but something even better than deep learning in case of the image visualization and voice recognition is called CNN, that is convolution neural network. See, we won't be able to do any programming assignments or exercise related to the ANN and CNN, because the the time it takes for training these models is it is a lot. So if I try to do those examples in the class, it will not be, so we won't be able to cover the problems. So if you want to see some programming examples, you can just Google YouTube in YouTube, and you will be able to see a lot of worked out examples in Python and all. What I will try to do, I don't know whether I will get time or not, but to the video that I will upload, this particular video, if I have time, I will give a link to the GitHub repository, or some lab notebook. I'll share a lab notebook and the data, in which I will do some of the deep learning and CNN. So you can check that on your own, but we will not do it in class. Okay, CNN, the convolution neural network. How does this work? Have I covered everything in CNN? Yeah. So how does this work? So this CNN has three important parts. That is convolution layer. So you can be confused because we didn't see any layers when we are talking about convolution and pooling. But I'll try to clarify about these things. So we have three important features in the CNN, that is convolution layer, pooling layer, and fully connected layer. Okay, so first of all, let's understand this convolution neural network through image visualization example. I hope everyone knows about pixels. So just briefly, if someone doesn't know, that whatever image that you see, even in the screen that you are looking at right now, this whole image is made up of small uh, blocks, in which the light intensities are varied and the whole picture is created. It is so the your screen right now, if you look at it uh, in terms of it is actually a matrix, in which each matrix has the value of whether to turn on or turn off for that particular. So if you are looking at the screen right now, you will be seeing something like this. The the matrix or the values inside this particular matrix will have a signal of turn on, and the side ones will have a signal of turn off or lower light. So pixel, your images are made up of pixel are nothing but some blocks arranged in matrix format, so to create a screen. Okay. Now, image visualization, when we do image recognition or digital processing, what we do is we manipulate the values in this matrix only. So let's say if you have a matrix 5 by 5, you have a very low resolution image, and it has only 5 by 5, 25 pixels. So this is an image, very worst quality image, but let's use this. Now when I talk about convolution layer and how does this convolution neural network works, so what you will do, you are going to give the model two values. One is tried, that is usually 1, so let's not worry about that, but you can change that. And one is the dimension of the filter matrix. Okay, now how does this work? Let's see. So you have a 5 by 5 image, and now we are talking about convolution. So what, based on these two parameters, your model is going to do, it is going to create a k by k matrix. Let's say our k in this case is 2, so it is going to create a 2 by 2 matrix. We call this as a filter matrix, and it will use this to go to each all the 2 by 2 combinations in your 5 by 5 frame. So first it is going to check these 2 by 2 points, 2 by 2 pixels. Then next, since you have given stride of 1, what does that mean? That when you are going to next, you shift by 1 pixel. So now it is going to these 2 by 2 pixels. And then next, these 2 by 2 pixels. And it is going to sweep through your image. So first row, if it has completed first row, then in the next row, these 2 by 2, let me use highlighter, these 2 by 2 pixels. And when it is doing that, it is also doing some kind of mathematical operation. So that's why this convolution layer or convolution is the most mathematically intensive part of this convolution neural network. Convolution maximum calculation. Okay, so you have made a 2 by 2 filter matrix. It is going to sweep through these pixels, and actually, maybe I should have talked about this. When you have an image, right? When you have an image, it let's say this 5 by 5 pixel only that we have. So the colors in the image, actually, when you look at in the matrix, will be denoted by some numbers. So let's say this number is one. Oh, why it is not there? 1, 7, 100. Some values it will be. So when you are using your filter matrix 2 by 2 and sweeping through your this original image, it is going to combine the value of the four pixels that it is looking at. It is going to combine these values with some weights and then give out a single value. So this is your image. When you did the convolution with a 2 by 2 filter at a stride of 1, so we will get one value for this particular four set of pixels. Then we will get one value for this four set of pixels. Then similarly we will get more and more pixels, and we will have another pixel or another matrix with ourselves. And now we are going to do operations into that. So this you can call as a new layer. I don't want to call this as a convolution layer. If you want to, if it is easier for you to remember, then you can call it that. But let's just, I will call it as a new layer. Now we can actually know or that how many elements are going to be there in this particular uh, new layer. So let's see how we can know. You can actually do manually. or you can use this formula that n or m, let's say this is an m by m square matrix. So always use a square matrix to keep your operation simple. You can do actually non-square matrix probably, but I have not seen it anywhere, so I'll not suggest you to do non-square matrix. Use a square matrix only. So what is this m? This m is nothing but, let's say this was an n by n, is n minus k plus 1. So keep the stride 1. In that case, your new matrix, that is the new layer that will be created after this convolution of this old layer, will be n, that is 5, minus k, that is 2 for our case, plus 1. So m is equal to 5 minus 2, 3, plus 1, 4. So luckily I made it correctly. We will have a 4 by 4 matrix, and each you can say pixel of this particular, or each entry of this matrix, will have some weighted sum of the values in the original 4 pixels of the matrix. Okay, so also when we talk about this filter, right, this filter having 4, then we just don't keep these filters like this. We actually give them their weightage. So this is your 2 by 2 filter that you will initialize and that you will train. So basically in our case, this particular yellow term would have gotten, and let's take this as an example for the values. Let's say this was 101, this was 50, and this was 90. So in this value will be 101 into W1 plus 50 into W2 plus 90 into W3 plus 100 into W4. So some kind of weighted average of this original 4 pixels with your filter will be assigned to the new layer. So I hope this is clear that how this convolution works. It is going to based on your given input, it is going to make a matrix of weights, and it is going to sweep through sequentially through your original image and give you one output based on the weights and the matrices input values. Okay, this is convolution, and this is one filter. Now, when we are talking about convolution neural network, you would have used iPhones and some other fancy technologies to do object detection. You would have seen that uh, it, it is actually detecting the camera or the photos. You are actually able to detect a bottle and a plant and a face, all these three things in the same time. So how does that work? That works by using multiple filters. Okay, so how do we do multiple filters? So as I said, in your first convolution, what you did, you used one matrix of 2 by 2 uh, size. Now you train this matrix to look for bottle. You create another matrix, same 2 by 2, and you train that matrix, because that matrix will have different weightages. So let's say this bottle matrix has W1, W2, W3, W4, and then the plant matrix has W1 dash, W2 dash, W3 dash, W4 dash, and the face matrix has W1 double dash, and so on. So you can use actually multiple filters to train or to identify multiple images in the same, or multiple objects in the same image at the same time. So that is why, if you remember, the image that Sir shared with you, it was one matrix, and then from that multiple matrices. I hope this is clear. So actually all these are looking for different things. This is looking for bottle, this is looking for plant, this is looking for space, this is looking for car, and so on. So you can look for multiple things. And what will happen now? Yeah, so these things will have some kind of z value, and actually in here also you use the ReLU activation function. So you won't have just directly the value of, let's say this was also z, let's say this was z. You use a ReLU function and you have the activation sequence either 0 or z. So you yeah, so either this, you can use activation function. Let's not go into that. So now what happens from your 2D kind of a matrix and image, now you have a 3D matrix, right? But each layer is telling whether there is a bottle or plant or face or car. Now here's the magic. Now comes the pooling. That is the most interesting part that I felt in convolution neural network. The amazing thing is now you have a 3D pooling. So you have a 3D matrix, you will have 3D pooling. Let's say in your image, and you have trained it. Let's say you have trained it. Let's say in your image here, even though it is a worst quality image, in this particular pixels, you had bottle, and in this 4 pixels, you had plant. Okay, let's say this is the case. Then your trained convolution neural network, if I extract this plant kind of new layer, the new layer that is generated after convolution for plant, you will see that, let's say it is 4 by 4 again, these will be more activated, these 4 or these 2 will be more activated, and your bottle new layer, these will be more activated. And what does pooling do? Pooling tries to combine all this 3D matrix again into 2D matrix. And how does it do that? It does that you can have a maximum pooling. So when you do a maximum pooling now, you will have this kind of information that in your, now again the 2D matrix, it will be the same size of that, it will just be 2D instead of being 3D. In this particular new matrix or array, you will have these things telling that this one is associated to bottle, and sorry, plant, and this one is associated to bottle. See, because training your matrix, training your features to identify bottle or plant is difficult. That's why we do them separately by creating different filters. Okay, but once you have trained them, then you combine them and tell this new array that here it is a bottle, here it is a plant. So this pooling, actually, one of the most common ways of pooling is max pooling. So you can actually understand what this max pooling actually means is that you look into this 3D matrix. All these will have 4 by 4. Now you look at this element. In this element, sorry, look at this element. The first corner of all these filters. Which one is more activated? Which one has the highest value? Take that value, give it to the new layer. Look at the next layer, so next pixel. Check which one has the highest value, which one is more activated. Take that value, give it to this. So maximum pooling is nothing but the maximum of this 3D matrix and giving it to the new 2D matrix. And after that you can again do as sir told, that now even if you don't want to go to the full stack, you can actually have again perform the convolution and again have some layers trained for something, and then again do the pooling and make it even smaller. You can do that, but let's just keep ourselves to one convolution. So what did one convolution do? To summarize, one convolution swept our original image. Let me just write it here. 100% drop that here. What did one convolution do? It swept through our original image with different filters for different object or features, and in doing so it created n maybe a 3D. It created a 3D matrix with each layer governed by each filter. And when you do that, after we do that, we do a pooling. So this was your convolution. Now this is pooling. Get the values of the maximum um, or the most activated pixel or filter for each pixel, and make a 2D matrix. So for each pixel you get the maximum value and get make a 2D matrix out of that. So this is what one convolution did. Now, is that clear till here? What we basically wanted to do, what we have basically done, because after that it's very simple. Okay, so if it is not it is little bit there is a doubt, then you can go back and watch it again and again. It will be helpful because it is not that frankly speaking, it is not that difficult, and I think you will be able to get it in second try if you have not understood it now. Okay, now after pooling is done, we go for fully connected layer. How do we do that? After pooling, we have only a 2D matrix, that is 4 by 4. What we do is we arrange each of these values into a single array. So if this is 1, 2, 3, just a minute, I think I'm missing something. Am I missing something? No, okay. Yeah. So 1, 2, 3, 4, 5, 6, 7, 8. So it will be arranged in one single array. 1, 2, 3, 4, 5, 6, 7, 8, and so on till 16. Now this looks familiar, doesn't it? What another way can we represent this? We can represent it like this, right? With the value for one being 1, 2, 3, 16. So after we have done the pooling and we have made our matrix size small, or we have consolidated our features into a 3 by 3 or 2 by 2 even matrix, square matrix, always keep it a square matrix, then we arrange it into a single array, and after that it's nothing but deep learning or neural network again. Then again you have these things connected to the other nodes, and then you have an output layer. What is the significance of this fully connected? See here, if you see this particular entry in this matrix, this particular entry was only connected with these four entries, right? And then some weights. So this is not, so this value is not influenced by all these other entries in the pixel, only this. That's why it is not fully connected. When we say fully connected, that's what we see in our neural network, that this neuron is affected by all these neurons through connection. So that's why we call that last part of the convolution neural network, that is nothing but neural network, as fully connected. Then again your weights matrix and bias matrix will come, and you use that to get the value of here z, and you can use the activation function, either ReLU or sigmoid function, and you can decide whether to activate this or not, and then based on that you can calculate the output. Okay, so this is fully connected layer. Okay, so is there anything I'm missing in the convolution network? Okay, one more thing. What did we do in pooling? We did nothing but getting the maximum of the pixel values, right? So that's why this pooling, even though it has hyperparameters, hyperparameters meaning, so I actually told you guys that we have a 4 by 4 matrix, and since we have, let's say, 5 filters, we have a 3D matrix that is 4 by 4 by 5. This is the 3D matrix, and out of that we created a 4 by 4 comma 1, a 2D matrix. So you can remove this 4 by 4 matrix, and each value is the maximum of all these 5 4 by 4 matrix. What you can do in pooling actually is something more than this. You can reduce the size here also. How? Same as this filter matrix, you can decide that I don't want my new matrix to be the same size as that of my old. What you can do is you can let's use these two matrices. You can choose that I want the maximum value out of these four elements in the set of my 3D matrix. So it is 4 by 4, but you say that I don't want a maximum value of single pixel and assign it to this, but I want a maximum value among these four pixels uh, from these five from these five filters, and based on that I want to give. So what will happen? Let's just see. Firstly firstly what will happen is, for this element, it is going to look for the maximum value in each filter. So let's say here bottle is there, so here some nice maximum value came in. There is no plant, there is no face, there is no car. So here also some maximum value came. Yeah, near some maximum value came, let's say zero point 0.1, and for face let's say 0.01, for car let's say zero point 0.5. Some values came, but for bottle it came 10. So then it at first took the maximum of these four elements, 4 pixels in the matrix for each filter, and then it took the maximum out of all the filters. So in that way also you can do. So if you don't have want to do individual pixels, you can do a set of pixels and you can assign that value here. And again, you have to traverse this throughout. So you can have a stride of 1, so now I want the maximum of these 4, or you can have a stride of 2 also, that after this I want directly these 4. I don't want this overlap, I want directly these 4. So that also uh, can be used. So that is why it is said that this pooling will have some hyperparameters. What are hyperparameters? Hyperparameters are something that we don't calibrate. Like here, this k 2 into 2, that matrix we decided, and the stride of 1 we decided. We can change these things and train our model, but when we are training our model, these things will not change. Only these weights will change. So the things that we manually give input and based on which we train our model, that are the hyperparameters. So in pooling also, you can have these hyperparameters of uh, how much size of the matrix you want, from which you want the maximum value, right? And how much stride you want. You can have hyperparameters, but you don't have trainable parameters here. No trainable parameters, because how we are getting just maximum, right? So maximum we cannot train the maximum value, so that's why it is not trainable. In pooling, no training is happening, but in fully connected, again, this matrix of weightage is there, and in convolution also the matrix of weightage is there for each filter, so there is training is happening. So that is basically CNN, how CNN looks like, how CNN works. Okay, I understand that it is difficult to understand, to learn this in one class. So you can go through some of the YouTube videos also, and you can solidify your concepts. I don't think that will be asked in the exam, but if you want, if you're interested, you can do that. I know that the instructor professor for this course is very enthusiastic about these learning neural network techniques. Okay, now that is done. I will recommend one channel. So you can go to Three Blue One Brown. I don't know if you have heard of it. YouTube channel. A very nice mathematician, very renowned mathematician. He has a YouTube channel, and he discussed or explained the neural network in two videos. A very nice graphical representation. You can go and check it out. Okay, so to conclude this session, we'll talk something about what different type of images are there, what are the scales. So when you have a monochromatic image, you have only white and black. That means 0 and 0 or 1. When you have a grayscale image, that is the black and white images or videos, the old TVs that used to show, then you have uh, variations between white and black. That is, gray also is there. Then how do we get that? Is we have from the intensity of this particular pixel can vary from 0 to 255, 0 being black and 255 being white. And so that means that from 0 to 255 it can take 256 different values. And how is that, uh, how is that possible? Because the value for this pixel is given by an 8-bit input. So you have 8-bit monochromatic input, actually. Let's say 1 2 3 4 5 6 7 8. So all these 8 inputs, all these 8 things can have an input of 0 and 1. And when you look at the number of terms or number of different terms that we can make from this, you will see that it is 2 power 8, which is equal to 256. So 256 different values can be generated from this 8-bit combination, and that are used to give to this particular pixel, and that's how we get a grayscale. When you want more scale, then it was said that there is 18, sorry, not 18, but 16-bit input is there. When you have high color format, that's the colorful pictures that we see. high color format. That is nothing but you have a 16-bit input, right? And then 2 power 16 is 65,536. That's what you would have seen in the slides. Okay. And then there are different type of color modes: red, green, blue, that is used for digital processing or digital image, and they are also called additive. Why they are called additive? Because when you add them, they don't become black, they become white. When you digitally, when you see the white color in the screen as of now, what you are seeing, this position here, a red LED, blue LED, oh, sorry, green LED and blue LED, they are glowing at their maximum intensity. So red is also 255, green is also 255, blue is also 255. That's how you see this white. Whereas there is another kind of color combination that will come when you try to print something or you try to paint. That is cyan, magenta, yellow, and then black. So you can just say CMY, but since CMYK was written, I'm writing it here. So this is for printing purpose or painting purpose, and it is a subtractive mode. Why subtractive? Because when you combine cyan, magenta, yellow in actual real life, they don't give white, they give black. That's why it's called subtractive. And then another color mode what this was discussed, that is much more apparent to us human beings, that is hue, saturation, and value. Saturation is nothing but chroma, that was discussed in the color scale that I think we talked about it in the last to last session, or last session, yeah, last session. So hue, value, and chroma, where hue actually describes which color band is predominant, whether it is red color is predominant, yellow color predominant, orange color predominant, which color is predominant. Saturation or chroma talks about the purity of that color. So we all have done image, editing to our photos before posting it to social media, right? So there you would have seen when you increase saturation, the colors become more vibrant, right? So that is what saturation represents. And then value is just when you try to increase or decrease the brightness. So light and dark. So these three, which are more understandable to human eye, this is also one of the color scale. It is represented nicely in the cylindrical format in the PPT. And there is one question also. There was one question in your week about which degree is your cyan located. I don't know whether that is important or not, but you can refer to that for the PPT for that. Yeah, so I think that is the topic, or these are the things that I wanted to discuss. The literature review of the different ways these things have been used, you can go through the papers. That is, I don't think that is going to be asked in the exam, so we'll not cover all those things. If you are interested, you can go through the papers and see how these techniques have been used to classify the organic content, the iron content, you know, or the soil texture in using the machine learning and image recognition. Yeah. So if you have doubt till here in anything, you can ask, and I'll try my best to answer. Okay. So sorry, Prachi. I am asking these NPTEL people. I have asked 3 4 times now, but I am not getting any positive response. The only response I got was in your announcement portal, the details of your examination will be released, but I don't see that till now. So I am not. I'm sorry. I'm not. I'll not be able to answer whether the exam will be subjective or objective. The only thing I can give you a hint. It is not 100% reliable, but I remember reading in the exam registration that you have to log into your system before giving the exam. So it's most probably an online exam, and in that case, when you are logging into system, you are not actually expected to type the answer. You may be expected to do some calculation and get the final answer, but most probably it is going to be MCQ. But I have not gotten an official response from the NPTEL team. Okay, so any other question regarding the topic that we just went through today? Okay, so look at the video. I will post this video in YouTube. Look at it once or twice, then you will be able to understand how the convolution and neural network works. Because these are the important, or all these things are important. This linear regression, but the world has moved to more exciting things. So you should also go and keep up with them. Okay, thanks you, thanks guys for this. Yeah, so we'll meet again next week.